Tonight, we're going to explore galaxies. Not just the one we call home, but some of the most amazing ones throughout the universe. We'll look at the quiet dwarf galaxies and massive spirals, even the broken pieces still bright from old cosmic crashes. We'll talk about invisible dark matter clouds, black holes that blink like far-off signals, and brand new galaxies glowing at the very edge of everything we know. Some of these things might seem strange or wonderful. Others could just settle into your mind gently, like a distant memory. But every single one is real. Each fact is a soft echo from the huge, never-ending story of space. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. When we consider the vastness of space, there are phenomena that truly stand out, challenging our everyday understanding of light and power. Among these, the quasar represents a particularly striking example. Imagine, if you will, a galaxy, a system of hundreds of billions of stars, planets, gas, and dust, all bound together by gravity. Now, picture something within that galaxy, so luminous, so intensely bright, that it completely overshadows all those countless stars combined. This is the essence of a quasar. It's a place where the central black hole of a galaxy becomes exceptionally active, transforming its immediate surroundings into one of the most brilliant beacons in the cosmos. At the very heart of most large galaxies, including our own, there lies a supermassive black hole. For the most part, these colossal objects are relatively calm, quietly sitting at their gravitational centers. But occasionally, a black hole will begin to feed, drawing in an immense amount of gas and dust from the surrounding galactic environment. As this material spirals inward, inexorably pulled by the black hole's immense gravity, it doesn't just fall straight in. Instead, it forms a rapidly rotating disk, a swirling maelstrom of matter. This structure is known as an accretion disk. The friction within this disk, generated by particles rubbing against each other at incredible speeds, causes the material to heat up to extraordinary temperatures. We're talking about millions of degrees, hot enough to emit light across the entire electromagnetic spectrum, from radio waves all the way to powerful X-rays and gamma rays. It's this superheated, rapidly moving material in the accretion disk, not the black hole itself, that generates the incredible luminosity of a quasar. The black hole is a region of spacetime from which nothing, not even light, can escape. It is fundamentally dark. However, the energy released by the gas before it crosses the event horizon, that point of no return, is truly immense. Photons, the tiny packets of light, are created in staggering numbers. They blast out into space, carrying away vast amounts of energy. This outward rush of radiation is so potent that it can outshine the combined light of every single star in its host galaxy. Think of a trillion suns, all burning at once, concentrated in a region not much larger than our solar system. That gives you a sense of the sheer power involved. Quasars are not just bright, they are also ancient. Because their light is so incredibly powerful, it can travel across immense cosmic distances. This means that when we observe a quasar, we are often seeing it as it existed billions of years ago. Its light has journeyed through the expanding fabric of space for eons, finally reaching our telescopes. This makes quasars like cosmic time capsules, offering us a glimpse into the early universe, a time when galaxies were younger, richer in gas, and their central black holes had abundant fuel to consume. The light we detect today from a quasar that is billions of light years away is essentially a snapshot from a distant past, showing us how that region of space glowed when the universe was still in its formative stages. In addition to the intense light from the accretion disk, many quasars also launch powerful jets of particles. These jets emerge from the regions close to the black hole, perpendicular to the accretion disk, and blast out into space at speeds approaching the speed of light. These are not merely streams of gas. They are highly collimated beams of energized particles, guided by intense magnetic fields that twist and focus the outward flow. These jets can extend for millions of light years, far beyond the visible boundaries of the host galaxy itself. They heat up the surrounding intergalactic gas, influencing the formation of galaxy clusters and even potentially regulating star formation in other nearby galaxies. So, a quasar represents a galaxy's central black hole in its most ravenous, most energetic phase. It's a temporary but spectacular display of cosmic power, fueled by the gravitational collapse of matter and radiating light across the universe. These active galactic nuclei, as they are technically known, are monuments to the hidden power of black holes, demonstrating how darkness can, paradoxically, become the source of the most brilliant light we can observe. They are reminders that the universe holds extremes of energy and scale that are truly difficult to grasp, silently burning for a time, before eventually dimming as their fuel supply dwindles, leaving behind a much quieter, more conventional galaxy. Moving on from these incredibly bright centers of distant galaxies, let's consider something closer to home, though still on a truly grand scale, our own Milky Way galaxy. It's a massive spiral, a home to billions of stars, including our Sun. But even our galaxy isn't a static, unchanging entity. It's constantly interacting with its neighbors, and sometimes those interactions involve a slow, cosmic meal. Right now, our Milky Way is in the middle of consuming a smaller companion, a process that has been unfolding over vast stretches of time. This companion is known as the Sagittarius dwarf spheroidal galaxy. It's a much smaller, fainter system compared to our majestic spiral, and it finds itself caught in the powerful gravitational embrace of the Milky Way. Think of it as a much larger, more massive object slowly, gently pulling apart a smaller one, bit by bit. The Sagittarius dwarf has actually passed through the main body of our galaxy multiple times over its long history. Each pass has been a disruptive event, with the Milky Way's immense gravity tugging at the dwarf galaxy's stars, gas, and dark matter. With every encounter, more of the Sagittarius dwarf's constituent parts are stripped away, pulled into the gravitational field of our larger galaxy. These stripped stars, once firmly bound within the Sagittarius dwarf, now form long, delicate streams that stretch out into space. They wrap around the Milky Way like ghostly, luminous ribbons, silent trails marking the path of the dwarf galaxy's slow disintegration. These stellar streams are faint, almost invisible to the naked eye, but with sensitive telescopes and careful analysis, astronomers can map their intricate patterns. They are like breadcrumbs left behind, showing the history of this ongoing cosmic digestion. The Sagittarius dwarf itself isn't completely gone yet. It still exists as a distinct, albeit diminished, entity. But it's clearly fading, its structure stretched thin, and its stars slowly being assimilated. It's unable to resist the overwhelming gravitational forces at play. The significance of this ongoing event extends beyond just watching a smaller galaxy being absorbed. The remains of the Sagittarius dwarf are actually helping scientists understand how the Milky Way itself grew over cosmic time. Our galaxy didn't simply form all at once, as a single, fully structured entity. Instead, it expanded and evolved through a process called accretion, slowly accumulating smaller galaxies, gas clouds, and dark matter over billions of years. Each such merger, each quiet consumption of a smaller system, added mass and stars to the Milky Way, contributing to its current size and complexity. What we observe when we look up at the night sky, the beautiful band of light that defines our galaxy, is the culmination of countless such events in the distant past. The Sagittarius dwarf is simply one of the more recent and currently observable instances of this continuous process. Even as we speak, our galaxy is still changing, still being reshaped by the material it draws in. These tidal forces, the gravitational stretching, are not violent in the way we might imagine a collision here on Earth. Instead, they are slow, sweeping, and persistent, unfolding over timescales that dwarf human comprehension. It's a quiet, ongoing transformation, a testament to the dynamic nature of galaxies, even our own familiar home among the stars. The universe is a constantly evolving place, and even the most seemingly stable structures like galaxies are part of that endless, silent dance. Now, let's turn our attention to another fascinating aspect of galactic evolution, one that involves the most mysterious objects in the universe: black holes. Specifically, supermassive black holes. We already know that most large galaxies host one of these behemoths at their core. But what happens when two galaxies, each with its own central supermassive black hole, decide to merge? It's a slow, grand cosmic event, and the black holes don't just immediately combine. Instead, when two galaxies come together, their respective supermassive black holes are drawn towards the center of the newly forming, larger galactic system. They don't instantly crash into each other. Far from it. What often happens is that they begin a complex, gravitational dance, forming a binary system of black holes. Two supermassive black holes, each with millions or even billions of times the mass of our Sun, orbiting each other. This orbital dance can be incredibly slow, taking millions of years, sometimes even hundreds of millions of years, to fully play out. They are caught in a gradual spiral, slowly drawing closer and closer over cosmic awns. Detecting these dual black holes is quite challenging for astronomers. They are often hidden deep within the dusty, crowded cores of merging galaxies. In some rare instances, both black holes might be actively feeding, like quasars we just discussed, each glowing brightly as separate points of intense light. This makes them a bit easier to spot. However, more often, they are less active, and astronomers have to look for indirect signs. These signs can include unusual patterns in the motion of nearby stars and gas, or subtle shifts in the light emitted from the galactic core, revealing the gravitational presence of not one, but two massive objects influencing their surroundings. These pairs of supermassive black holes are a natural and expected part of how galaxies evolve. Mergers are a fundamental process by which galaxies grow and change. And when galaxies merge, their central engines, their black holes, must eventually merge too. The final stages of this cosmic waltz involve the emission of gravitational waves. As the two black holes spiral closer and closer, their immense masses create ripples in the very fabric of space-time, much like throwing a stone into a pond creates ripples on the surface. These gravitational waves carry away energy, causing the black holes to draw even closer, faster and faster, until they ultimately coalesce into a single, even more massive supermassive black hole. This ultimate merger is an incredibly energetic event, releasing an enormous burst of gravitational radiation that ripples across the universe. While the final act of merging is relatively quick in cosmic terms, the preceding orbital dance is prolonged and silent. Until that climactic moment, these binary black holes orbit quietly, hidden deep within the heart of their new, combined galaxy. They are like twin hearts, beating in a single, colossal chest, holding untold power and posing many unanswered questions for scientists, seeking to understand the most extreme gravitational events in the universe. Their existence underscores the dynamic and transformative nature of galactic evolution, where even the most fundamental structures can undergo profound changes over billions of years. Now, let's consider something even more profound and, in a way, unsettling: the existence of galaxies that appear to be made of almost nothing we can directly see. Imagine vast cosmic structures, undeniably real, yet completely devoid of the usual markers of a galaxy. No bright stars, no glowing clouds of gas, not even clusters of stars to give them form. And yet, they are held together, bound by a powerful, invisible force. These are the dark matter galaxies. These enigmatic systems are composed almost entirely of dark matter, that mysterious substance that astronomers believe makes up about 27% of the universe's mass, vastly outweighing all the visible matter combined. Unlike normal matter, dark matter doesn't interact with light in any way. It doesn't absorb, emit, or reflect it. This makes it inherently invisible to our telescopes, regardless of the wavelength we use. So, how do we even know these dark matter galaxies exist? We find them not by their light, but by their gravity. The presence of these dark galaxies is revealed through their gravitational effects on other objects. One way astronomers detect them is by observing how they subtly bend the light from more distant galaxies located directly behind them. This phenomenon is called gravitational lensing. Even though the dark matter galaxy itself is unseen, its immense gravitational mass distorts the path of light traveling from beyond it, creating a quiet, almost imperceptible distortion that reveals its invisible bulk. It's like seeing the presence of an invisible pane of glass by the way it slightly warps the image of objects behind it. Another method involves observing their influence on neighboring galaxies. A dark matter galaxy, even though it doesn't shine, still exerts a gravitational tug on any nearby visible galaxies. By carefully measuring the motions of these visible galaxies, astronomers can infer the presence and mass of an unseen, gravitationally influential neighbor. Sometimes, they are revealed through subtle patterns of motion, ripples left in nearby gas clouds, or unusual velocity discrepancies that cannot be explained by visible matter alone. The origin of these dark matter galaxies remains one of the universe's quietest puzzles. Scientists aren't sure how they formed. They might be failed galaxies, systems that gathered enough dark matter to form a gravitational well but, for some reason, never accumulated enough normal gas to ignite significant star formation. Perhaps their gas was stripped away early on, or it simply never cooled down enough to collapse into stars. Alternatively, they could be the ghostly remnants of other galaxies, long since erased by interactions, leaving behind only their dark matter halos. Whatever their true nature, these dark matter galaxies drift through the immense expanse of space like silent, invisible shadows. They are like hidden islands of gravity, vast structures with no light at all, challenging our fundamental definition of what a galaxy truly is. Their existence emphasizes how much of the universe is still beyond our direct perception, composed of components that operate under different rules than the familiar world of light and matter. They are quiet testaments to the hidden architecture of the cosmos, hinting at depths of mystery that we are only just beginning to explore. While we often think of galaxies as fixed, unchanging structures, especially our own Milky Way, the reality is far more dynamic. Even the largest galaxies are not isolated entities, they are constantly interacting with the broader gravitational field of the universe. Our Milky Way, for instance, is currently being gently, but persistently stretched apart by the gravitational influence of its neighbors. These are known as cosmic tides, a phenomenon that might sound familiar from Earth's oceans, but here, it plays out on an unimaginably grand scale. The primary culprit in this cosmic stretching of our galaxy is the massive Andromeda Galaxy, our nearest large galactic neighbor. Andromeda is not just sitting still, it's drifting towards us across the vast cosmic void, inexorably drawn by mutual gravitational attraction. As these two colossal galaxies approach each other, their immense gravitational fields begin to exert forces on one another. This creates a differential pull, meaning that the side of the Milky Way closer to Andromeda feels a stronger tug than the side farther away. This difference in gravitational force is what we call a tidal force. Over millions of years, these tidal forces have subtly warped the shape of our galaxy's outer disk. They've created gentle waves and ripples in the majestic spiral arms that define the Milky Way. Individual stars, though immense distances apart, are nudged slightly from their usual orbital paths. Vast clouds of gas, the raw material for future star formation, shift and drift under this persistent, silent pull. It's not a violent tearing apart, but rather a slow, sweeping reshaping of our galactic home. Imagine a vast, delicate fabric slowly being pulled and stretched by invisible hands. This process is a constant reminder that no structure in the universe, no matter how vast or seemingly stable, exists in isolation. Everything is interconnected, everything is influenced by the gravitational fields of everything else. The Milky Way, with its hundreds of billions of stars, is not immune to these universal forces. It is part of a larger cosmic tapestry, woven with threads of gravity that link it to other galaxies and galaxy clusters. These cosmic tides illustrate the ongoing evolution of galaxies. Our home is not a finished product, but a constantly changing entity, subtly reshaped over eons by the gravitational whispers of its neighbors. It's a quiet testament to the pervasive influence of gravity, a force that acts across unimaginable distances and over timescales that humble our brief existence. Even as we drift through space, seemingly unaware, our entire galaxy is responding to these external pulls, a subtle yet profound reshaping that continues in the quiet rhythm of the cosmos. When we think of galaxies, our immediate frame of reference is often our own Milky Way. It's undeniably enormous, stretching over 100 Zalozan light years from one edge to the other and containing hundreds of billions of stars. It feels vast, almost incomprehensibly large. But in the grand scheme of the universe, our galaxy is actually quite average, even modest, in size. There are other galaxies out there that dwarf the Milky Way, making it seem small by comparison. Consider, for instance, a galaxy like IC 1101. This is one of the largest known galaxies in the observable universe, and its scale is truly mind-boggling. It stretches more than 6 million light-years across. To put that into perspective, that's more than 100 times the diameter of our own Milky Way. Imagine a celestial object so immense that if our galaxy were placed inside it, it would be but a tiny speck. This sheer scale challenges our ability to truly comprehend size and distance in the cosmos. These colossal galaxies are typically elliptical in shape, lacking the distinct spiral arms of our Milky Way. They are often found at the very centers of massive galaxy clusters, where the density of galaxies is highest. And they didn't get so big by simply forming stars in isolation. Their immense size is the result of a long and violent history of galactic cannibalism. Over billions of years, these giant ellipticals have consumed dozens, perhaps even hundreds, of smaller galaxies. Each merger, each slow absorption of a less massive system, added more stars, more gas, and more dark matter to their growing bulk. Their cores are incredibly dense, packed with ancient, red, aging stars that have been around for most of the universe's history. As you move outward from the core, their light gradually fades into the surrounding darkness, where lonely stars orbit in vast, slow, almost solitary circles, remnants of the countless galaxies that were absorbed. These supergiant elliptical galaxies are relatively rare, but their existence underscores the extreme scales that gravity can create in the universe. They are quiet giants, slowly evolving and accumulating mass over cosmic timescales. Trying to truly grasp the size of something like IC 1101 is an exercise in humility. It reminds us that our own Milky Way, while spectacular and immense from our perspective, is merely a middle-sized inhabitant of a universe filled with structures of truly staggering proportions. These giant galaxies are not just bigger. They represent a different mode of galactic evolution, driven by repeated mergers and a long history of gravitational dominance. They sit like silent, colossal monarchs at the heart of their clusters, slowly gathering everything around them, enduring through aeons, and showcasing the quiet power of accretion on the grandest possible scale. Most galaxies, including our own, form new stars at a relatively leisurely pace. The Milky Way, for example, gives birth to perhaps 1 or 2 new stars per year, on average. It's a steady, ongoing process, but certainly not a frantic one. However, there are some galaxies that experience periods of truly explosive star formation, where new stars burst into existence at an astonishing rate. These are known as starburst galaxies. In a starburst galaxy, the rate of star formation can be hundreds, or even thousands, of times faster than in a typical galaxy like the Milky Way. Imagine hundreds or even thousands of new suns igniting every single year, all within the same galactic system. This incredible burst of activity is fueled by exceptionally dense clouds of gas. These gas clouds, rich in the raw ingredients for stars, collapse under their own gravity at an accelerated rate, leading to a sudden, widespread ignition of stellar nurseries. These dramatic outbursts of star formation are often triggered by specific cosmic events, most commonly collisions or close encounters between galaxies. When two galaxies pass through each other, or even just brush by, their gravitational fields disturb and compress the gas within them. This compression acts like a cosmic switch, forcing the gas into denser regions, which then rapidly collapse to form stars. The result is a sudden and intense blaze of activity. The galactic core, or specific regions within it, light up with a vibrant glow of ultraviolet light emanating from hot, young, massive stars. There's also a significant amount of hot dust and glowing gas, indicators of rapid star birth. However, this furious pace of star formation cannot last indefinitely. Starburst galaxies burn through their available gas fuel incredibly quickly. The very process of forming so many massive stars also leads to a high rate of supernova explosions, which can further disrupt and expel gas from the galaxy, effectively quenching further star formation. So, while they shine briefly and brilliantly, like cosmic fireworks illuminating the deep expanse of space, this phase is short, lived in astronomical terms, lasting only a few million years. After this intense period, once the gas is mostly consumed or blown away, the galaxy settles back into a much calmer, more sedate existence. For a little while, though, these starburst galaxies are among the brightest objects in the observable universe. Their intense glow provides astronomers with unique opportunities to study star formation under extreme conditions. They are a powerful reminder that galactic evolution is not always a slow, gradual process. It can involve moments of sudden, spectacular transformation, where a galaxy briefly ignites with a dazzling display of new life, before eventually fading into a quieter, more mature form. These galaxies showcase the raw energy and dynamic nature of the cosmos, where even immense structures can undergo dramatic, short-lived bursts of activity. Let's now consider the very heart of galaxies once again, specifically the supermassive black holes that reside there. Our own Milky Way, as we've discussed, hosts one of these gravitational giants known as Sagittarius A. It sits quietly at our galactic center, weighing in at about 4 million times the mass of our Sun. It's a truly massive object, but it's not the largest one in our immediate cosmic neighborhood. That distinction belongs to the supermassive black hole at the core of the Andromeda galaxy. Andromeda, our closest large galactic neighbor, is a spiral galaxy similar in many ways to the Milky Way, but it's actually larger and more massive. And its central black hole reflects that greater mass. The supermassive black hole in Andromeda is at least twice as massive as Sagittarius A, possibly much more, with estimates placing it at around 100 million solar masses. This makes it a truly formidable gravitational anchor, silently dominating the core of its host galaxy. Currently, both Sagittarius A and Andromeda's black hole are relatively quiet. They are not actively consuming large amounts of matter, so they don't shine with the intense brilliance of a quasar. They are mostly dormant, their immense gravitational fields silently holding sway over their immediate surroundings. However, it's very likely that in the distant past, both black holes went through more active phases, perhaps even blazing as quasars, when their galaxies were younger and had more gas available for consumption. The universe is dynamic, and even these quiet giants can awaken. Looking far into the future, a truly monumental event awaits these two galactic behemoths. In about 4 billion years, the Milky Way and the Andromeda Galaxy are destined to collide and merge. This will be a slow, majestic process, unfolding over hundreds of millions of years. And when these two galaxies combine, their central supermassive black holes will also begin a long, gravitational dance. They will slowly spiral towards each other, losing energy through interactions with stars and gas, and eventually through the emission of gravitational waves. This cosmic tango will culminate in the ultimate merger of the two black holes into a single, even more massive object. Imagine a black hole with the combined mass of our Sun 104 million times over, silently sitting at the heart of a new, colossal elliptical galaxy. This future galaxy, sometimes playfully dubbed Milkomeda by astronomers, will be the new home for the stars and dark matter of both original galaxies. The merger of their black holes will be a final act in this grand cosmic drama, a powerful testament to the transformative power of gravity. So, at the heart of these two approaching galaxies, two colossal gravitational entities silently await their eventual union. Two galaxies, two immense hearts of darkness, destined to become one, shaping the future of our galactic neighborhood in a way that is both inevitable and awe-inspiring. It's a quiet future, waiting in the deep darkness of space, a reminder of the slow, profound changes that constantly reshape the universe around us. One of the most profound and humbling aspects of astronomy is the realization that when we look out into the deep reaches of space, we are inherently looking back in time. This is because light, despite its incredible speed, still takes a finite amount of time to travel across the vast cosmic distances. The implications of this are truly astonishing. The light from the most distant galaxies our telescopes can detect has been journeying through the universe for over 13 billion years. Think about that for a moment. This light began its incredible voyage when the universe itself was incredibly young, only a few 100 million years old, long before our Sun or Earth even existed. When this ancient light finally reaches our detectors, it shows us these galaxies not as they are now, in their present, more evolved state, but as they were in that incredibly distant past. They appear as tiny, faint smudges in telescope images, their light redshifted by the expansion of the universe, a phenomenon we'll discuss in more detail later. They are ancient, primordial objects, glowing with the light of the first generations of stars. These early galaxies were very different from the grand, organized spirals and ellipticals we see in our local universe today. They were typically smaller, more chaotic, and often rich in gas and dust, undergoing rapid bursts of star formation. Many were in the very early stages of assembling themselves, like cosmic building blocks, just beginning to coalesce. Their stars were often what astronomers call metal poor, meaning they contained very few elements heavier than hydrogen and helium. As heavier elements are forged over time in the cores of stars and then dispersed through supernovae, these first generations of galaxies played an absolutely crucial role in shaping the universe we inhabit today. They were the pioneers, the first significant sources of light that ended what astronomers call the cosmic dark ages. Before these galaxies ignited, the universe was largely a dark, neutral expanse of hydrogen gas. The intense ultraviolet radiation from the hot, young stars in these early galaxies ionized, this neutral hydrogen, stripping away its electrons and making the universe transparent to light. They also form the initial seeds for the much larger galaxy clusters that would eventually emerge. The fact that they're faint, ancient light has managed to reach us across such immense stretches of space and time is a testament to the perseverance of light itself and the incredible power of our modern telescopes. Each tiny smudge is a window into the universe's infancy, a precious glimpse of a time when the cosmos was still figuring itself out, laying the groundwork for everything that followed. We are literally watching the past unfold, one photon at a time, connecting us directly to the earliest moments of cosmic history. It's a quiet, profound way to witness the universe's grand narrative, written in the oldest light we can possibly perceive. Our Milky Way galaxy, that vast, magnificent spiral we call home, didn't simply appear fully formed in its current state. Like all large galaxies, it grew and evolved over billions of years, slowly accumulating mass and stars. A significant part of this growth involved a process of cosmic digestion, where our galaxy merged with and consumed smaller, less massive galaxies. And each time it did, it left behind subtle, almost invisible clues, thin, luminous streams of stars stretched out across the galactic halo like quiet, ghostly trails. These are known as stellar streams. They are the lingering remnants of long, lost galaxies that were pulled apart by the immense gravitational forces of the Milky Way. As a smaller galaxy is drawn in, our galaxy's gravity exerts a differential pull, stretching the smaller system into these long, elongated structures. The stars, once tightly bound within their original galaxy, are now spread out, following long, looping paths that spiral around the main body of the Milky Way. They are invisible to the naked eye, lost in the general glow of our galaxy, but sensitive telescopes and advanced data analysis can detect these faint, diffuse ribbons of ancient stars. Some of these stellar streams are still relatively intact, representing the more recent acts of galactic cannibalism. For example, the remnants of the Sagittarius dwarf spheroidal galaxy, which we discussed earlier, are currently being absorbed and form some of the most prominent stellar streams around our galaxy. Others are incredibly ancient, so old that their stars have become widely dispersed, forming diffuse, almost ethereal ribbons of light that are incredibly challenging to detect. These represent mergers that happened billions of years ago, with the stars having had ample time to spread out and blend into the overall galactic halo. Mapping these stellar streams is a crucial task for astronomers. It allows them to literally trace the Milky Way's history, acting like cosmic archaeologists discovering the fingerprints of past collisions and mergers. Each stream tells a story: the direction from which the smaller galaxy approached, the strength of the gravitational interaction, and the timescale over which the absorption occurred. They provide invaluable insights into how our galaxy assembled its mass, not through one sudden event, but through a long, quiet process of accretion, drawing in its neighbors over immense stretches of time. The sky around us, seemingly static and unchanging, is in fact full of this quiet, slow motion. We are continually drifting through the echoes of events that happened billions of years ago, surrounded by these faint, luminous whispers of devoured galaxies. These stellar streams are a testament to the dynamic nature of galactic evolution, a continuous process of growth, interaction, and transformation that has shaped our cosmic home into the magnificent structure we see today. They are silent archives, holding the memories of long, gone systems within the vast, slowly turning tapestry of the Milky Way. The future holds a truly spectacular, though incredibly slow, cosmic event for our Milky Way galaxy. In about 4 billion years from now, our galaxy and its nearest large neighbor, the Andromeda Galaxy, are destined to collide and merge. This won't be a sudden, catastrophic impact in the way we might imagine two cars crashing. Instead, it will be a slow, majestic gravitational dance, unfolding over hundreds of millions of years, transforming both galaxies into a single, new entity. Andromeda is already approaching us. Its motion through space is bringing it closer to the Milky Way at a remarkable speed of nearly 100 kilometers per second. While this sounds incredibly fast, the distances involved are so immense that it will still take billions of years for the two galaxies to truly engage. Eventually, they will pass through one another. The individual stars within each galaxy are so incredibly far apart that direct collisions between stars will be extremely rare, almost negligible. However, the vast clouds of gas and dust within the galaxies will collide, compressing and stirring up the material, likely triggering intense bursts of new star formation. As the galaxies pass through each other, their immense gravitational fields will exert powerful forces, disrupting their elegant spiral shapes. Spiral arms will tangle, stretch, and deform, creating long, sweeping tails of stars and gas that are flung out into intergalactic space. The galaxies may swing past each other several times, each close encounter further distorting their structures, until eventually, the gravitational forces bind them together into a single, more stable configuration. Over many hundreds of millions of years, this combined system will settle down. The organized, flat disk structure of the original spiral galaxies will largely be erased, and the stars will adopt more random, elliptical orbits. The end result is expected to be a much larger, roughly elliptical galaxy, a new home for the combined stellar populations of both the Milky Way and Andromeda. Astronomers have even given this future galactic entity a playful name, Milkomeda. Our own solar system is expected to survive this grand merger. While its position within the newly formed Milkomeda galaxy will undoubtedly change, shifting to a different part of space, the Sun and its planets are unlikely to be directly impacted by a stellar collision. It's a quiet kind of drama, playing out on a scale of time and distance that is almost beyond human comprehension. And though the most dramatic phase is still billions of years away, the gravitational interaction has already begun, subtly influencing the motions of both galaxies as they inexorably drift towards their shared future. It's a testament to the constant, slow reshaping of the universe, where even the whole universe is being reshaped, slowly, quietly, but always. Now, let's explore some truly peculiar types of galaxies, ones that almost defy our usual expectations of what a galaxy should be. We tend to picture galaxies as sparkling islands of light, filled with countless stars. But in the deep, quiet stretches of space, there are systems that seem to have almost no stars at all. These are, in essence, ghostly galaxies, made primarily of cold hydrogen gas. They drift through the universe like immense, dark clouds, barely detectable, if at all, through conventional optical telescopes. Imagine looking out into space and seeing a structure as large as a galaxy, yet it emits almost no visible light. There's no bright star formation, no clusters of young, luminous stars to illuminate its vast expanse. Instead, these systems are composed mostly of cold, atomic hydrogen gas. Hydrogen is the most abundant element in the cosmos, the fundamental building block of stars. Yet, in these specific galaxies, it hasn't coalesced efficiently enough to ignite into stars. They exist, they have mass, and they move, but they remain largely unlit. Because they lack significant numbers of stars, these dark galaxies, as astronomers sometimes call them, don't announce their presence with brilliant starlight. You can't just point a regular telescope at them and expect to see a glowing spiral or a fuzzy elliptical. They are, for all intents and purposes, invisible in the wavelengths of light that our eyes can perceive. Their existence was a puzzle for a long time, and their true nature is still something scientists are trying to fully grasp. So, If they don't shine in visible light, how do we even know they are there? The key lies in their primary constituent, hydrogen gas. Cold hydrogen gas, even when it's not forming stars, still emits a very faint, specific radio signal. This signal is known as the 21-centimeter line, or the hydrogen line. It's caused by a subtle change in the energy state of the hydrogen atom's electron. By tuning into this particular radio frequency, astronomers can detect these otherwise invisible clouds of gas, even across vast cosmic distances. Radio telescopes become our eyes, allowing us to perceive these silent structures that would otherwise be lost to us. These radio emissions reveal not only their presence, but also crucial information about them: their mass, how they're rotating, and their motion through space. This data helps us understand the hidden gravitational fields at play, hinting at the distribution of dark matter within these gas-rich systems. Without this radio astronomy, many of these strange, faint objects would likely have remained undiscovered, forever hidden in the background of the cosmos. The origins of these dark galaxies are still a subject of much debate and wonder among scientists. One leading idea is that they might be failed galaxies. Perhaps they started to form in the early universe, accumulating enough dark matter and gas, but then something prevented them from effectively forming stars. Maybe their gas was somehow stripped away by powerful winds or gravitational interactions before it could condense. Or perhaps the gas never cooled sufficiently to collapse into dense enough pockets for star birth to begin. Another possibility is that they are the gastric remnants of past galactic collisions or mergers. When galaxies interact, gas can be flung out into space, sometimes coalescing into new, smaller systems that are mostly gas with very few stars. In some scenarios, star formation might have been shut down early in their history or never truly ignited in the first place, leaving them as vast, dormant clouds. They float through the immense emptiness of space like quiet, dark potential. They possess mass, they have internal structure, and they move through the universe according to the laws of gravity. But without the radiant glow of stars, they remain almost invisible, mere cold clouds of hydrogen gas waiting. Waiting for what? Perhaps for a future interaction that might compress their gas and finally ignite star formation. Or perhaps they are simply destined to drift on, forever unlit, a strange and silent phase in the long, diverse life cycle of galaxies. Their existence highlights how diverse galaxies can be, and how much of the universe operates beyond the realm of visible light. They are a testament to the hidden aspects of cosmic existence, reminding us that there are still countless mysteries to uncover, drifting quietly in plain sight, waiting for the right tools to reveal their subtle glow. These silent systems represent a kind of invisible potential, a vast but unlit part of the cosmic tapestry, challenging our understanding of what defines a galaxy in the first place. They are a quiet whisper in the vastness, a shadow in the light-filled cosmic dance, yet undeniably real. Just as some galaxies are invisible due to their lack of stars, others reveal themselves not through their own direct light, but through a profound distortion of the light coming from objects much farther away. This remarkable phenomenon is called gravitational lensing, and it's one of the most powerful tools astronomers have at their disposal. Imagine a heavy object, like a massive galaxy or a cluster of galaxies, positioned between us and an even more distant object, such as another galaxy or a quasar. According to Einstein's theory of general relativity, this massive foreground object will warp the fabric of space-time around it. As light from the more distant background object travels through this warped space-time, its path is bent, much like light passing through a glass lens. This bending of light can produce truly spectacular effects. Sometimes, the light from a single distant galaxy can be bent and magnified into multiple images, appearing as mirror duplicates of the original. Other times, it can be stretched into long, luminous arcs, or even a perfect, shimmering ring around the foreground lensing galaxy, a phenomenon known as an Einstein ring. It's as if the foreground galaxy is acting like a natural cosmic magnifying glass, revealing objects that would otherwise be too faint or too far away for our telescopes to detect directly. The beauty of gravitational lensing is that it allows us to spot galaxies that are otherwise incredibly difficult to see. Some of these foreground lensing galaxies might be intrinsically faint, perhaps composed mostly of dark matter, or so dusty that their visible light is almost completely obscured. Yet, their immense gravitational mass is undeniable, and that mass is what creates the lensing effect. By observing the distorted light of background objects, we can infer the presence and properties of these invisible or hidden lensing galaxies. This technique has been instrumental in discovering some of the most distant and earliest galaxies in the universe. Imagine trying to see a tiny, faint firefly at the far end of a football field. Now imagine that firefly's light passing through a giant, invisible magnifying glass halfway down the field. That magnifying glass makes the firefly appear larger and brighter, bringing it into view. That's essentially what gravitational lensing does for cosmologists. It provides us with a natural boost, allowing us to peer further back in time and space than we could with our telescopes alone. Gravitational lensing also offers a unique way to weigh galaxies and map the distribution of dark matter. Since the amount of light bending is directly proportional to the mass of the lensing object, astronomers can analyze the degree of distortion to calculate the total mass of the foreground galaxy or cluster, including its invisible dark matter component. It provides compelling evidence for the existence of dark matter, as the visible matter alone is never enough to account for the observed lensing effects. So, these lensing galaxies aren't just passive objects in space, they are active participants in our cosmic observations. They transform into natural telescopes, magnifying and distorting the universe behind them. By carefully studying the paths of the light they bend, we gain invaluable insights not only into the distant, background galaxies, but also into the very nature and composition of the lensing galaxies themselves. It's a quiet, profound interaction between light and gravity, where space itself becomes a tool, revealing hidden structures and pushing the boundaries of our cosmic vision. The universe is a curved place, and this curvature, this bending of light, allows us to see what would otherwise remain forever unseen. At the very heart of many galaxies, particularly the larger ones, reside those supermassive black holes we've been discussing. When these black holes are actively feeding, drawing in gas and dust from their surroundings, they don't just produce the dazzling light of a quasar. Sometimes, they unleash something even more dramatic and far-reaching, powerful jets of matter that blast out into space. These jets are truly colossal, stretching for millions of light years, far beyond the confines of their host galaxy. It's important to remember that these jets don't originate from inside the black hole itself. Nothing can escape the black hole once it crosses the event horizon. Instead, these jets are formed from the superheated material in the accretion disk, the swirling, incandescent gas and dust that surrounds the black hole. Intense magnetic fields, generated within this rapidly rotating disk, become twisted and coiled. These powerful fields act like a cosmic nozzle, focusing and accelerating particles away from the black hole's poles. They effectively create twin beams of highly energetic particles that are launched outwards at speeds approaching the speed of light. When these jets erupt, they pierce through the surrounding gas and dust of the galaxy, and then continue onward, extending into the vast emptiness of intergalactic space. In radio images, which capture the emissions from these energetic particles, they appear as immense, glowing threads or lobes, sometimes symmetrically extending for staggering distances on either side of the galaxy's core. They are among the largest known structures generated by individual objects in the universe. These jets are not just a spectacular display. They have a profound impact on their environment. As they blast through space, they heat the surrounding intergalactic gas, influencing the properties of galaxy clusters and even potentially regulating star formation across vast distances. The energy they inject into the intergalactic medium can prevent gas from cooling and collapsing, thereby suppressing the birth of new stars in nearby galaxies or even within the host galaxy itself. It's a striking thought these colossal jets, stretching for millions of light years, all originate from a region that, by cosmic standards, is incredibly tiny, much smaller than our entire solar system. It's a brilliant, concentrated point where matter meets gravity, and in that extreme environment, light and energy are unleashed in ways that reshape the cosmic landscape. These powerful outflows demonstrate the incredible feedback mechanisms that exist between a galaxy's central black hole and its wider environment. They are quiet engines of immense power, silently shaping the largest structures in the universe, all from a tiny, brilliant point in the dark. When we talk about the beginning of the universe, the Big Bang, it's often followed by a period described as the Cosmic Dark Ages. This was a time when the universe was filled with mostly neutral hydrogen and helium, and there were no stars or galaxies to light it up. It was a profound period of darkness. Then, slowly, over hundreds of millions of years, the first structures began to coalesce. Gas cooled, condensed under gravity, and the very first stars ignited. Following these pioneering stars, the earliest galaxies began to take shape, bringing an end to that long era of cosmic night. The oldest known galaxy we've ever found offers us an incredible glimpse into this foundational period. Its light has traveled for over 13 billion years to reach our telescopes, meaning we are observing it as it existed just 320 million years after the Big Bang. That's an incredibly short time in the universe's history, a mere cosmic blink. This ancient galaxy is small and relatively young, filled with the light of its newly born stars. What's particularly striking is that even at such an early stage, it appears surprisingly well formed, suggesting that galaxy assembly began very rapidly after the Big Bang. Observing galaxies from this incredibly early epoch helps astronomers piece together what the universe was like when the very first galaxies were taking shape. These nascent systems were often chaotic, clumpy, and likely quite short-lived, burning through their fuel quickly. Yet they were the building blocks, the foundational structures that would eventually merge and evolve into the majestic galaxies we see today. Their light, though faint and incredibly redshifted due to the universe's expansion, carries invaluable information about the conditions of the early cosmos, the properties of the first stars, and the initial stages of galaxy formation. With each new generation of powerful telescopes, like the James Webb Space Telescope, we are able to look a little farther back in time, a little deeper into this cosmic dawn. We can't see these ancient galaxies with perfect clarity. They appear as tiny, faint smudges, but every photon collected from them is a precious whisper from the universe's infancy, a silent story of how everything began. They represent the first sparks of light, the initial attempts at structure and order in a universe that was just starting to find its way. And in that faint, distant glow, we find the story of everything that would eventually follow, connecting us to the very origins of cosmic light. Our own Milky Way galaxy, vast and complex as it is, wasn't built in a single, sudden event. Instead, it grew over billions of years through a process of gradual accumulation, merging with and absorbing countless smaller galaxies. And each time this happened, these ancient mergers left behind subtle clues that astronomers can still detect today. These clues take the form of invisible stellar streams, delicate ribbons of stars that were once part of those devoured galaxies. Imagine a smaller galaxy, a dwarf system, slowly being drawn into the gravitational embrace of the much larger Milky Way. As it spirals inward, the powerful tidal forces exerted by our galaxy begin to stretch and pull it apart. The stars that once belonged to the dwarf galaxy are gradually stripped away, not violently, but in a long, slow process. These liberated stars then continue to orbit within the Milky Way's hollow, but they follow paths that are distinct from the native stars of our galaxy. They form long, thin streams that loop and spiral around the galactic center, like ghostly trails marking the path of their former home. These stellar streams are, for the most part, invisible to the naked eye. The individual stars are too faint and too spread out to be easily distinguished against the luminous background of the Milky Way. However, through meticulous observation with powerful telescopes and sophisticated data analysis, astronomers can identify these patterns. By studying the precise motions and chemical compositions of millions of stars in the galactic halo, they can pick out the ones that don't fit the general pattern, the ones that bear the fingerprints of a different origin. Some of these streams are relatively young, such as the prominent remnants of the Sagittarius dwarf galaxy, which we are still actively absorbing. These are more defined and coherent. Others are incredibly ancient, dating back billions of years, so old that their stars have become very diffuse, spread out across vast regions of the halo, making them even harder to detect. They are like faint, whispered memories of long-lost systems. Mapping these stellar streams is a vital tool for understanding the Milky Way's history. By reconstructing the paths and properties of these streams, astronomers can trace the timeline of past galactic collisions, identify the original galaxies that were absorbed, and gain insights into how our galaxy acquired its current mass and structure. It's like finding the archaeological record of our galaxy's growth, written in the faint, quiet motion of ancient stars. The sky around us is subtly dynamic, constantly shaped by these past events, and we are still drifting through the quiet echoes of those colossal, slow-motion mergers. Our galaxy, the Milky Way, is not alone in the universe. It's a prominent member of a relatively small galactic neighborhood that astronomers call the Local Group. This group is a collection of more than 50 galaxies, all gravitationally bound to each other, spread across an expansive region of about 10 million light-years. The two dominant members of this cosmic family are, of course, our own Milky Way and the slightly larger Andromeda galaxy. A third, smaller spiral galaxy, Triangulum, is also a significant member. The vast majority of the other members of the Local Group are dwarf galaxies. These are much smaller systems, often irregular in shape, containing only a few million to a few billion stars each. Many of these dwarf galaxies orbit the larger ones, like celestial moons around planets, slowly circling their massive hosts over billions of years. Other dwarf galaxies in the Local Group float more freely in the outer regions, less directly bound to either the Milky Way or Andromeda. These galaxies within the Local Group are not static. They constantly interact with one another through their mutual gravitational pulls. Over immense timescales, they tug on each other, merge, and exchange stars and gas. These interactions are a key part of galactic evolution, influencing the shapes and compositions of all the members. The Local Group itself is just a tiny part of a much larger cosmic structure, the Laniakea supercluster, but it represents our immediate galactic family, the collection of systems with which we share a common gravitational destiny. Each galaxy within this group, no matter how small or faint, has its own unique story, its own history of star formation, and its own internal dynamics. Yet, they are all bound together by the invisible threads of gravity, moving through space as a cohesive unit. It's a quiet gathering of galaxies, a cosmic neighborhood where interactions unfold slowly, subtly, and continuously, shaping the future of each member as they drift together through the vastness of the universe. The local group is a microcosm of galactic interactions, a small corner of the cosmos where the grand processes of cosmic evolution are playing out right on our doorstep. We often think of our Milky Way as the quintessential galaxy, the most important one since it's our home. And it is indeed a grand and enormous spiral. But within our own local group, the immediate cluster of galaxies to which we belong, the Milky Way isn't actually the biggest. That honor goes to the Andromeda Galaxy, our majestic neighbor, located just over 2 million light-years away. Andromeda is a spiral galaxy very similar in appearance to the Milky Way, with sweeping arms and a bright central bulge. However, it's significantly more massive and generally larger in diameter. While the Milky Way is estimated to contain around 200–400 billion stars, Andromeda is thought to harbor closer to 1 trillion stars, making it a truly colossal system. Its central supermassive black hole is also considerably larger than ours, and its surrounding halo of dark matter extends much farther into space. Both Andromeda and the Milky Way are the dominant gravitational players in the local group. They are locked in a slow, inevitable gravitational embrace that is drawing them closer and closer. As we mentioned earlier, Andromeda is currently approaching us at a speed of about 110 kilometers per second. This mutual attraction will culminate in that grand galactic merger in a few billion years, forming the new, larger elliptical galaxy, Milkomeda. Even though Andromeda appears as just a faint, fuzzy blur in the night sky to the unaided eye, it is an incredibly vast and intricate system, teeming with stars, star clusters, gas clouds, and undoubtedly planets. It's a galaxy full of its own mysteries, its own history, and its own potential for life. In many ways, Andromeda is our galactic twin, a cosmic mirror reflecting many of the features of our own galaxy, yet surpassing us in sheer scale. Understanding Andromeda is crucial to understanding our own galactic future. Its immense size and mass mean it will play the dominant role in the upcoming merger, effectively absorbing the Milky Way into its structure, even as they combine to form something entirely new. So, while the Milky Way is our cherished home, it's important to quietly acknowledge that the largest galaxy in our immediate cosmic family is the magnificent Andromeda, a silent giant drifting ever closer, destined to become an even greater part of our galaxy's future self. Surrounding every large galaxy, including our Milky Way, there exists something profoundly mysterious and completely invisible, a dark matter halo. This isn't just a faint, diffuse region, it's an immense, spherical cloud of dark matter that extends far beyond the visible boundaries of the galaxy's stars, enveloping it like an unseen shroud. This halo doesn't emit any light, it doesn't reflect light, and it doesn't absorb light. It is utterly transparent to all forms of electromagnetic radiation, making it impossible to observe directly with any telescope. However, its gravitational influence is undeniable and absolutely crucial to the existence of galaxies as we know them. Astronomers first uncovered the evidence for these dark matter halos by studying how galaxies rotate. When they measured the speeds at which stars orbit the center of a spiral galaxy, they made a puzzling discovery. Stars located in the outer regions of the galaxy were moving much faster than they should have been, based on the amount of visible matter. The stars, gas, and dust that could be seen. According to the laws of gravity, if only the visible matter were present, these fast, moving outer stars should have simply flown off into intergalactic space. But they didn't. They remained gravitationally bound to the galaxy. The only logical explanation for this discrepancy was that there had to be a significant amount of extra mass present, providing additional gravitational pull to hold everything together. This hidden mass, which doesn't interact with light, is what we now call dark matter. It's a mysterious form of matter that, despite its invisibility, accounts for the vast majority of the mass in the universe, outweighing normal, visible matter by a factor of more than 5 to 1. Without these massive dark matter halos, galaxies simply wouldn't hold together. The gravitational pull from the visible stars and gas alone would be insufficient to keep the rapidly orbiting stars and gas clouds from scattering into space. It's believed that galaxies initially formed dullars within these dark matter halos. The halos acted as gravitational scaffolding, providing the necessary mass and gravitational wells to draw in normal gas and dust, which then cooled and condensed to form stars and the visible structures of galaxies. So, while we can't see these halos with our eyes or our most powerful telescopes, we know they are there. They are the invisible skeletons upon which galaxies are built. They shape how galaxies grow, how they move, and how they cluster together to form the vast cosmic web. The universe, in its quiet, profound way, is held together by things we haven't yet directly seen, by a mysterious, unseen substance that silently dominates the cosmos, shaping everything we know and observe. The dark matter halo is a silent guardian, an invisible embrace that cradles and defines every major galaxy in the universe. If you happen to live in the southern hemisphere, you might occasionally catch a glimpse of two peculiar, hazy patches of light in the night sky. For centuries, people wondered what these clouds were, but they are not atmospheric phenomena. They are, in fact, entire galaxies. These are the Large Magellanic Cloud and the Small Magellanic Cloud, two irregular dwarf galaxies that are gravitationally bound to and slowly orbiting our Milky Way. These two galaxies are relatively close to us, cosmically speaking. The Large Magellanic Cloud is about 160,000 light-years away, and the Small Magellanic Cloud is a bit farther, at around 200,000 light-years. Both contain millions of stars, along with numerous star clusters and vast clouds of gas and dust. The Large Magellanic Cloud, in particular, is home to one of the most active and spectacular star-forming regions in our galactic neighborhood, a massive nebula known as the Tarantula Nebula. This region is a bustling stellar nursery, constantly giving birth to new, hot, massive stars. Astronomers believe that these two Magellanic Clouds are relatively recent additions to our Milky Way's gravitational influence, possibly captured into orbit within the last few billion years. Their orbits around our galaxy are complex and dynamic, and they are also interacting with each other, their mutual gravity causing distortions and influencing their internal structures. As they circle the Milky Way, our galaxy's powerful gravitational pull is slowly but surely tugging at them, stripping away some of their stars and gas. For now, they remain distinct, separate galaxies, appearing as brilliant, irregular patches of light that slowly drift across the southern sky. They are small companions, ancient travelers on long, looping paths through the vast galactic halo of the Milky Way. But this state of affairs won't last forever. Over immense stretches of time, the relentless gravitational forces of our galaxy will continue to pull at them, gradually drawing them closer and closer, eventually leading to their absorption and merger into the Milky Way. These Magellanic Clouds are not just beautiful sights, they are invaluable laboratories for astronomers, allowing us to study galaxy interactions and star formation processes in a relatively nearby setting. Their presence, their slow dance around our galaxy, and their eventual fate are all part of the ongoing, quiet story of galactic evolution, a testament to the continuous reshaping of our cosmic neighborhood. They are bright, irregular, and temporary guests, slowly being drawn into the embrace of their much larger host. As the Magellanic Clouds continue their slow, gravitational dance around the Milky Way, they don't move without leaving traces. Just as a ship leaves a wake behind it in the water, These dwarf galaxies leave quiet, almost imperceptible evidence of their journey through space. These are long, faint trails of gas and stars that stretch across the sky, remnants of material stripped away by the Milky Way's powerful gravity. The most famous of these is called the Magellanic Stream. It's an immense, thin ribbon of neutral hydrogen gas that wraps around the Milky Way, stretching for hundreds of thousands of light years behind the two dwarf galaxies. This stream formed as the Milky Way's tidal forces, its differential gravitational pull, tugged on the gas within the Magellanic Clouds, gradually drawing it out and sweeping it into a vast, elongated structure. This gas is too diffuse to form stars on its own, so it glows only faintly in specific radio wavelengths, revealing its ghostly presence. In addition to the gas stream, there are also stellar streams. These are made up of individual stars that have been pulled loose from their original homes within the Magellanic Clouds. These stars, now freed from their parent galaxies, continue to orbit the Milky Way, but they follow paths that align with these long, sweeping trails. They are incredibly faint and spread out, making them difficult to detect, but they are there, silent witnesses to the ongoing gravitational interactions. These trails are incredibly valuable to astronomers. By mapping their precise positions and motions, scientists can learn a great deal about the shape and strength of the Milky Way's gravitational field, especially in its outer halo. They also provide a direct, visual record of how galaxies interact over vast stretches of cosmic time. They are like cosmic footprints, subtle and slowly fading, but clearly revealing the long path taken by these dwarf galaxies through deep space. Even though the large and small Magellanic Clouds are still intact, for now, these streams serve as a powerful reminder that galactic orbits are rarely simple, isolated paths. They are complex, dynamic interactions that leave long, drifting echoes behind them. These quiet traces of gas and stars tell a story of gravitational tugs and pulls, of material being exchanged and repurposed, all unfolding in the silent, immense theater of our galactic neighborhood. They are a testament to the continuous, subtle reshaping of the universe, where even quiet movements leave lasting marks across billions of years. Galaxy clusters are among the largest known structures in the universe, truly immense gatherings of hundreds or even thousands of individual galaxies. These colossal collections are all bound together by gravity, forming dense cosmic cities in the vast expanse of space. However, when astronomers first tried to calculate the total mass of these clusters based solely on the visible matter, the stars, gas, and dust they could observe, they ran into a major problem. The visible mass was nowhere near enough to provide the gravitational pull required to hold the cluster together. Without additional, unseen mass, these clusters should have simply flown apart long ago. This profound discrepancy was one of the earliest and strongest pieces of evidence for the existence of dark matter. Something else, something invisible, had to be providing the vast majority of the gravitational force. That something else is dark matter. Although it doesn't interact with light and cannot be directly seen, dark matter constitutes the bulk of the mass in galaxy clusters. It acts as the invisible glue, holding all the galaxies in place and slowing their motions, ensuring the cluster remains stable over billions of years. We can't observe dark matter directly, but its presence is overwhelmingly evident through its gravitational effects. For instance, the way individual galaxies move within a cluster provides clues. Their speeds are far too high to be explained by the visible matter alone, requiring the presence of an unseen gravitational anchor. Similarly, the way light from even more distant background objects bends as it passes through the cluster, a phenomenon called gravitational lensing, reveals the total mass of the cluster, showing a significant excess over what visible matter can account for. Furthermore, the hot, X-ray emitting gas that fills the space between galaxies within a cluster, known as the intracluster medium, also provides evidence. The temperature and distribution of this gas are consistent with it being confined by a much stronger gravitational field than visible matter alone could provide. Without the immense hidden mass of dark matter, these grand clusters would not exist. They would simply dissipate into the cosmic background. Instead, they have remained gravitationally bound for billions of years, enduring as colossal islands of light in a dark ocean, all held together by a mysterious form of gravity that we still cannot fully explain. Their stability is a silent, powerful testament to the pervasive and essential role of dark matter in the architecture of the universe. Galaxies don't just exist in isolation or in small groups. They are part of a hierarchical structure that extends to the very largest scales of the universe. Groups of galaxies, like our local group, gather into much larger collections called galaxy clusters. And those clusters, in turn, are components of something even grander: superclusters. These superclusters represent the largest known structures in the cosmos. Imagine sprawling regions of space, hundreds of millions of light years across, filled with thousands upon thousands of galaxies. These galaxies are connected not by direct contact, but by the subtle, pervasive pull of gravity and by the underlying framework of dark matter. Superclusters are not solid, rigid objects. Instead, they are loose associations of galaxies, clusters, and groups, all moving through space together, subtly influenced by each other's gravity. Their shapes can vary enormously. Some appear like vast walls or sheets of galaxies, stretching across immense distances. Others are arranged in long, filamentary structures, like cosmic threads weaving through space. And at the intersections of these filaments, you often find the densest galaxy clusters. These structures are not static. Some superclusters are slowly collapsing inward under their own immense gravity, while others are still expanding with the general expansion of the universe. Our own Milky Way galaxy, nestled within the local group, is part of one of these superclusters. When we look out into the universe, in every direction, we see superclusters upon superclusters reaching out across the observable cosmos. These immense structures took billions of years to form, sculpted by the relentless action of gravity on the tiny initial density fluctuations that were present shortly after the Big Bang. Over cosmic time, these slight imbalances were amplified, drawing matter together into these colossal webs and filaments. Superclusters are not merely big, they represent the boundaries between vast cosmic realms, defining the largest patterns in the universe. They are a profound reminder of the organized, structured nature of the cosmos on its grandest scales. The very existence of such immense, interconnected systems speaks to the long, quiet process of cosmic evolution, where gravity slowly but surely shapes matter into ever larger, more complex arrangements. They are the grand architecture of the universe, silent and majestic, guiding the flow of galaxies across unimaginable expanses of space and time. In a fascinating redefinition that occurred in 2014, astronomers gave us a new perspective on our cosmic address. They found that our Milky Way galaxy, along with its local group companions and many other nearby galaxy clusters, are all part of an even larger, previously unrecognized supercluster. This colossal structure was given the name Laniakea, a Hawaiian word that means immeasurable heaven or vast heaven. It's a truly fitting name for an entity that stretches more than 500 million light years across and contains over 100 zeros and galaxies. Laniakea isn't shaped like a neat sphere or a simple blob. Instead, it's a vast and intricate network of cosmic filaments, much like the branches of a tree or the tendrils of a web. Along these invisible lines of gravity, galaxies are flowing, almost like rivers of light, all moving towards a central, incredibly massive region. This gravitational focal point is known as the Great Attractor. It's an immense, diffuse concentration of mass that exerts a powerful gravitational pull on everything in its vicinity, essentially guiding the motion of our local universe. The discovery of Laniakea fundamentally changed our understanding of where we live in the cosmos. We're not just in a galaxy, or a small group of galaxies. We are part of this much grander supercluster, a vast and organized system of cosmic flows. The gravitational well of the Great Attractor influences the motion of thousands of galaxies, including our own. It's a silent, unseen hand, gently but inexorably pulling us along a specific trajectory through the universe. This revelation serves as a powerful reminder that even our vast Milky Way is not an isolated island in space. It is intimately connected to a much larger, hidden, and quietly beautiful cosmic structure. Laniakea represents the largest boundary of our immediate cosmic neighborhood, a testament to the fact that the universe is far more interconnected and organized than we might initially perceive. It's a quiet, scientific discovery that offers a profound sense of place, grounding us within an immense, flowing tapestry of galaxies, all moving together in a silent, grand design. When astronomers map the distribution of galaxies on the very largest scales, they discover something truly remarkable. Galaxies are not just randomly scattered throughout space. Instead, they arrange themselves into a vast, interconnected network, a cosmic architecture known as the cosmic web. This web is composed of long, thin, thread-like filaments of dark matter and gas, stretching across hundreds of millions of light years. Imagine these filaments as immense, invisible highways, along which galaxies are strung like pearls on a necklace. These threads connect the densest regions of the universe, the galaxy clusters and superclusters, forming a complex, three-dimensional web with glowing nodes of galaxies at the intersections. In between these luminous threads lie immense cosmic voids, vast, empty regions where almost nothing exists. These voids are like the quiet, dark spaces within the intricate structure of the web. The shape and structure of this cosmic web were not accidental. They were seeded in the earliest moments of the universe by tiny, quantum fluctuations in density that occurred shortly after the Big Bang. Over billions of years, these minuscule variations were amplified by the relentless pull of gravity. Where matter was slightly denser, gravity pulled in even more matter, forming the filaments and clusters. Where matter was sparser, the expansion of the universe caused those regions to become even emptier, creating the voids. Galaxies, being concentrations of normal matter, form where the density of dark matter and gas is highest. Along these filaments and at their intersections, they move along these hidden strands, following the gravitational contours of the cosmic web like travelers on unseen roads. When we look out into space, we are not just seeing individual stars and galaxies. We are perceiving this grand, delicate, yet immensely powerful pattern that stretches far beyond what any single observation can encompass. The universe, even in its profound silence, possesses an intricate structure, a vast web of existence that guides the flow of galaxies across cosmic time. The universe isn't uniformly packed with galaxies. In fact, most of it is a profound emptiness. Between the great, luminous filaments of the cosmic web, there are vast regions that contain very little matter at all. These are the cosmic voids, immense, dark expanses that are almost entirely empty. Some of these voids are tens of millions of light years across, while others stretch for hundreds of millions of light years. Within these regions, you might find a few stray, isolated galaxies drifting slowly, but for the most part, they are silent, barren landscapes. These cosmic voids are, quite literally, the emptiest places we know in the universe. They formed naturally as matter in the early universe, driven by gravity, began to clump together into the filaments and clusters we just discussed. As matter gathered in some regions, it left behind vast, underdense areas that expanded at a slightly faster rate, gradually growing into these immense voids. It's a natural consequence of gravity's relentless work over billions of years, creating both the dense structures and the vast emptiness between them. Studying these voids is incredibly important for astronomers. They provide crucial insights into the expansion of the universe and the behavior of dark energy, the mysterious force believed to be accelerating the cosmic expansion. The size and distribution of voids can tell us about the initial conditions of the universe and how gravity has acted on those conditions over time. In a way, these voids define the cosmic web just as much as the luminous galaxies do. They are not merely the spaces in between, they are an integral part of the universe's large-scale structure, giving shape and context to the visible matter. They are quiet, dark, and almost untouched by the flow of time, vast regions where the universe seems to hold its breath. The profound emptiness of these voids serves as a powerful reminder of the sheer scale and diversity of the cosmos. While galaxies burst with light and activity, the voids represent the silent, unlit majority of the universe's volume, a vast, dark canvas upon which the luminous cosmic web is painted. They are a testament to the fact that even absence can be a significant feature of the universe, shaping its evolution and offering unique clues to its deepest mysteries. While most galaxies gather together in groups, clusters, or along the vast filaments of the cosmic web, there are some that choose a path of profound solitude. These are the cosmic hermits, galaxies that drift alone in the immense expanse of space, far removed from any dense cluster or prominent filament. They exist in a state of deep isolation, sometimes found on the very edges of cosmic voids and occasionally even deep within them. Imagine a galaxy, complete with its billions of stars and its own gravitational field, existing without any nearby neighbors to pull on it, collide with it, or stir its internal structures. Without the constant gravitational interactions that shape most galaxies, these isolated systems tend to evolve more quietly, at their own pace. Their star formation rates might be steadier, less prone to the sudden bursts triggered by mergers. Their shapes are less likely to be disrupted or warped by tidal forces, and their gas clouds remain largely undisturbed, slowly collapsing to form stars over eons. The exact reasons why these cosmic hermits formed in such lonely places are still a subject of scientific inquiry. Some may have been ejected from dense clusters long ago, flung outwards into intergalactic space, during particularly violent multi-galaxy encounters. Others might have simply formed in regions of very low density from the very beginning, in parts of the early universe where matter was naturally sparser, preventing them from ever joining a larger group. Whatever their origin, these isolated galaxies move through space with no close companions, experiencing a unique kind of cosmic solitude. In a universe where so much is connected, where gravity constantly binds and reshapes structures, these lone galaxies stand as quiet exceptions. They remind us that even on the grandest scales, within the vast, interconnected tapestry of the cosmos, profound isolation still exists. They are silent wanderers, moving through the dark, unlit by the proximity of neighbors, yet undeniably present, each a self-contained island of stars, living out its long life in quiet independence. Their existence underscores the incredible diversity of galactic environments and fates within the immense universe. Before the launch of the Hubble Space Telescope, our view of the universe was limited by Earth's atmosphere, which blurs light and distorts images. When Hubble was finally placed into orbit, high above the atmospheric interference, astronomers were eager to see what it could reveal. In the late 1990s, they made a bold decision to point the telescope at a seemingly empty patch of sky. This wasn't just any empty patch. It was a region with no known bright stars, No visible galaxies, nothing that suggested anything of interest. They then let Hubble collect light from this region for days, gathering every faint photon. The results were absolutely astonishing. What came back from that empty patch of sky was not darkness, but thousands upon thousands of galaxies packed into a tiny, almost imperceptible dot of space. This groundbreaking image became famously known as the Hubble Deep Field, and later, even deeper observations created the Hubble Ultra Deep Field. These images completely revolutionized our understanding of the cosmos. They showed unequivocally that no matter where we look, space is teeming with galaxies. Every pinprick of sky, no matter how unremarkable it seems to the naked eye, holds multitudes of galaxies, stretching back billions of years in time. Some of the galaxies in these images were relatively large and bright, closer to us in cosmic terms. But many were tiny, faint smudges, representing ancient galaxies whose light had been traveling for more than 13 billion years to reach Hubble's detectors. Together, these countless galaxies revealed the incredible richness, depth, and sheer abundance of the universe. It transformed our perception of the cosmos from one that might have seemed sparsely populated in distant reaches to one that is densely packed with luminous structures across all observable scales. The Hubble Deep Field images were more than just pretty pictures. They were profound scientific insights. They changed how we understood the distribution of matter, the history of galaxy formation, and the sheer scale of cosmic existence. What once appeared empty was suddenly revealed to be full of light, intricate structure, and a deep, layered history. The deeper we are able to look, the more galaxies we find, each one a silent testament to the vast and ever-present cosmic tapestry. These images are like cosmic archaeological digs, unearthing layer after layer of galactic history, showing us that the universe is far more densely populated and complex than we ever imagined. Building upon the legacy of the Hubble Deep Field, even more advanced observations have pushed the boundaries of our vision even further. Imagine holding a single grain of sand at arm's length. That tiny patch of sky, almost imperceptible, is roughly the area covered by the Hubble Ultra Deep Field. And within that minuscule sliver of the cosmos, our most powerful telescopes have revealed an astonishing sight, nearly 10,000 galaxies. Each one of these galaxies is an entire system filled with its own stars, planets, and a unique history stretching back through cosmic time. Some of these galaxies are relatively nearby and appear bright and well-defined in the images, but the majority are faint, distant smudges representing ancient galaxies whose light has journeyed for over 13 billion years to reach us. These are galaxies from the universe's infancy, seen as they were when the cosmos was just a few 100 million years old. The image is a breathtaking layered history, a cross-section of the universe at different epochs, from the early days of galaxy formation right up to the present. This single, deep image tells us something incredibly profound about the universe. If such a tiny patch of sky, equivalent to a grain of sand, holds so many galaxies, then the entire observable universe must contain hundreds of billions, if not trillions, of galaxies in total. This immense number challenges our intuition and underscores the sheer scale of cosmic existence. Every point of light, no matter how small or faint, represents a vast system, a universe unto itself. These deep images are far more than just photographs, they are genuine time machines. They allow us to peer into the past, to witness the universe as it was in its youth, and to study the evolution of galaxies across cosmic history. By analyzing the properties of these ancient, distant galaxies, astronomers can piece together the story of how the universe grew and changed, from its first chaotic beginnings to the richly structured cosmos we inhabit today. They are silent, luminous archives, reminding us how much remains to be discovered and how interconnected we are to the vast, ancient story of everything. Let's return to the topic of quasars, those incredibly luminous galactic cores powered by feeding black holes. While they are fascinating objects today, their prevalence has changed dramatically over cosmic time. Today, quasars are relatively rare. Most large galaxies, including our own Milky Way, host supermassive black holes that are largely quiet and dormant, not actively consuming enough matter to shine with quasar-like brilliance. However, if we could look back in time to the early universe, the situation would be entirely different. Quasars were far more common in that ancient epoch. The young universe was much richer in gas and dust, and galaxies were frequently colliding and merging. These conditions provided an abundant supply of fuel for the central black holes. During this period, many supermassive black holes grew incredibly rapidly, blazing forth as powerful quasars for millions of years. Some of the brightest quasars we have observed today existed when the universe was less than 1 billion years old. When we detect their light, we are seeing them as they were then, tiny but intensely luminous points of light that once lit up entire regions of space. Their powerful radiation wasn't just a spectacle, it had a significant impact on their surroundings. The intense energy could heat and ionize vast amounts of gas, potentially altering the structure of nascent galaxies and even halting star formation in some regions by blowing away or heating up the necessary gas. Eventually, as the universe aged, the supply of available gas in many galaxies dwindled. The frequent mergers became less common, and the black holes consumed most of their readily available fuel. As a result, these active cores went dark, settling into the quiet, dormant state we largely observe today. What remains are the quiet galaxies, the relics of once burning cores, their inner engines now mostly at rest. Quasars, therefore, are more than just bright objects, they are echoes of a brighter, younger universe, still visible across cosmic time, whispering stories of a more energetic and chaotic past. They offer a unique window into the early, transformative stages of galactic evolution, when the cosmos was undergoing its most dramatic changes. For a long time, astronomers believed that quasars were incredibly stable, burning brightly with a consistent luminosity for millions of years before gradually fading into quiescence. The process of a supermassive black hole consuming matter and emitting such vast amounts of energy was thought to be a slow, steady, and long-lasting affair. However, recent observations have challenged this view, revealing a more dynamic and surprising reality. We have now witnessed galaxies where the brightness of their central quasar flickers dramatically, changing its luminosity not over millions of years, but in a matter of just a few years, days, or even hours. These enigmatic objects are known as changing-look quasars. Imagine a distant galaxy that, one year, shines with the intense, blinding energy of an actively feeding black hole, radiating across the spectrum. Then, the very next year, or sometimes even within months, it dims significantly, as if someone had subtly turned down the cosmic volume control. In some truly astonishing cases, these quasars have even been observed to switch back again, reigniting their brilliance after a period of quietude. Astronomers believe this rapid flickering and dramatic change in luminosity happens when the flow of gas and dust into the central black hole undergoes sudden, significant alterations. Perhaps there's a sudden surge of new material falling in, causing a rapid increase in the accretion rate and a corresponding flare in brightness. Or, conversely, a blockage or disruption in the inner part of the accretion disk could temporarily starve the black hole of fuel, leading to a rapid dimming. It could also be related to changes in the magnetic fields that funnel material towards the black hole. Whatever the precise cause, these changing-look quasars tell us that the process of black hole feeding can be far more dynamic and episodic than previously thought. The heart of a galaxy, a region of immense gravity and power, can flare and fade on timescales that are surprisingly short, even on human timescales, rather than solely on the vast cosmic scales we usually associate with galactic evolution. It means that even something as massive and powerful as a quasar can experience moments of sudden quiet and equally sudden, brilliant light. These observations remind us that the universe is full of surprises, and that even our most fundamental assumptions about cosmic objects can be overturned by new, unexpected data, revealing a more intricate and dynamic reality. Quasars, as we've discussed, are among the most luminous objects in the universe, and their incredible brightness allows us to see them across truly immense distances. But because light takes time to travel, looking at these distant quasars means we are also looking far back in time. The light from many of the quasars we observe today began its journey before our own solar system had even formed, and certainly before the Milky Way galaxy had fully taken on its modern spiral shape. Many of the quasars we detect lie over 10 billion light-years away. This means that their light has been traveling through the expanding fabric of space for more than 10 billion years, crossing unimaginable cosmic voids and densities to finally reach the detectors in our powerful telescopes. What we are seeing, then, is not how these quasars appear in the present day, but how they existed when the universe was significantly younger, often less than a quarter of its current age. That ancient light has been stretched, or redshifted, by the ongoing expansion of the universe and dimmed by the sheer distance it has traversed. Yet, despite these effects, it still carries the unmistakable signature of extreme energy. This radiation, emanating from the superheated accretion disk around a voraciously feeding black hole, was once so powerful that it outshone every star in its host galaxy combined. Looking at a quasar, therefore, is like peering through an incredibly long tunnel that stretches through both space and time. It connects us directly to a younger, more energetic universe, to a kind of intense brightness that we no longer commonly observe in our immediate cosmic neighborhood. Nearby, large galaxies tend to have quieter, dormant black holes. These ancient quasars serve as invaluable probes of the early cosmos. Their light can pass through intervening gas clouds and galaxies, allowing astronomers to study the composition of the universe at different epochs. They are silent, distant beacons, each photon a message from billions of years ago, carrying information about a time when the universe was a very different place. Their existence is a powerful testament to the vastness of cosmic time and the enduring journey of light, bridging the gap between our present and the universe's distant, luminous past. Galaxies are not static objects merely floating in space. They are dynamic systems, and one of their most fundamental characteristics is rotation. Their countless stars orbit the galactic center, pulled by gravity, and this motion creates a delicate balance. However, in some galaxies, this rotation becomes quite extreme. The stars in their outermost regions whip around at such incredibly high speeds that, based on the visible matter alone, they should simply be flung off into the emptiness of space. Yet, they remain gravitationally bound. This surprising observation was one of the key pieces of evidence that first led astronomers to hypothesize the existence of dark matter. In the 1970s, pioneering astronomer Vera Rubin and her colleagues meticulously measured the rotation curves of spiral galaxies. They expected to see stars farther from the center orbiting slower, much like planets orbiting the Sun. But what they found was that stars in the outer parts of these galaxies were orbiting just as fast, or even faster, than stars closer to the center. This flat rotation curve was a profound anomaly. According to the established laws of gravity, if only the visible matter's stars, gas, and dust were present, the gravitational pull in the outer regions would be too weak to hold these fast, moving stars in their orbits. they should have simply flown off. The only way to explain this observation was if there was a vast, unseen halo of additional mass surrounding and permeating the galaxy. This invisible mass provided the extra gravitational pull needed to keep the outer stars bound. That hidden mass is what we now call dark matter. Dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes. But it exerts gravity, and that gravity is powerful enough to hold galaxies together, even when their visible components are spinning at hundreds of kilometers per second. It's a quiet, invisible balancing act, the outward momentum of rapidly orbiting stars perfectly counteracted by the inward pull of an unseen gravitational force. The faster the visible stars move, the stronger the invisible arms of dark matter must be, holding them close. This unexpected rotation curve was a pivotal moment in cosmology, revealing that the universe is composed of far more than meets the eye. It showed that galaxies are not just collections of luminous stars, they are deeply embedded within and shaped by vast, invisible halos of dark matter. This discovery transformed our understanding of galactic structure and evolution, highlighting the profound and essential role of a mysterious substance that silently orchestrates the motion of billions of stars, keeping them from spinning out of control. Most galaxies spin in a fairly straightforward manner, like a flat disk rotating around its center. But the universe is full of strange and wonderful exceptions. Imagine a galaxy that has a second, distinct ring of stars and gas orbiting around it, but this ring is oriented almost at a right angle to the main galactic disk, like a hula hoop spun around someone's waist. These remarkable systems are known as polar ring galaxies, and they are incredibly rare and visually striking. A polar ring galaxy essentially consists of two distinct components: a main, central galaxies, which is usually an elliptical or a lenticular, disc-shaped galaxy without prominent spiral arms, and a separate, outer ring of stars, gas, and dust that orbits perpendicular, or nearly perpendicular, to the central galaxy's equatorial plane. This creates a beautiful, almost surreal appearance, like one galaxy wearing another as a luminous halo. These unusual structures are believed to form through very specific types of galactic interactions. The most common theory suggests that a polar ring forms when a smaller galaxy, rich in gas, passes close to or even punches directly through a larger, more massive galaxy. During this close encounter or collision, the smaller galaxy is often torn apart by the larger galaxy's tidal forces. However, some of its material, gas, dust, and stars, can be left behind and captured by the larger galaxy's gravitational field. This captured material doesn't immediately merge with the main disk. Instead, if the geometry of the encounter is just right, this debris can settle into a stable orbit around the poles of the host galaxy, eventually flattening out into a distinct, rotating ring. Studying polar ring galaxies provides astronomers with unique insights into several key areas of galactic research. They are excellent laboratories for understanding how galaxies merge and interact, showing the complex aftermath of such events. They also offer valuable clues about the shape and distribution of dark matter halos. The stars and gas in the polar ring are orbiting in a different plane than the main galaxy, and their motion can reveal the gravitational influence of the unseen dark matter halo from a different perspective, helping to map its three-dimensional structure. These two distinct rotating systems, the main galaxy and its polar ring, move independently, like layered currents flowing in deep space. From a distance, they can indeed look like cosmic wheels, turning gracefully across two different axes, elegant, stable, and wonderfully strange. They are quiet, visual testaments to the complex and diverse ways in which gravity shapes galactic structures, creating objects of unique beauty and scientific intrigue. They remind us that the universe is far more inventive than we might initially imagine, capable of producing celestial arrangements that challenge our conventional notions of galactic form. When we think of galaxies, we typically envision either grand spirals with sweeping arms or smooth, featureless ellipticals. But the universe holds architectural surprises, and one of the most intriguing is the galaxy shaped like a giant cosmic donut. These are known as ring galaxies, characterized by a bright, prominent loop of stars, gas, and dust encircling a relatively empty central core. They stand out dramatically from the more common galactic forms. These distinctive shapes are typically the result of a very specific and violent cosmic event, a galactic collision. But not just any collision. Ring galaxies are often formed when a smaller, more compact galaxy punches directly through the center of a larger, gas-rich disk galaxy. It's not a gentle graze, it's a direct hit. As the smaller galaxy plunges through the larger one, its gravitational force creates a powerful disturbance, sending shockwaves rippling outward through the larger galaxy's gas and dust. This outward, moving gravitational wave acts like a cosmic snowplow, compressing the gas and dust into a dense, expanding ring. This compression then triggers a rapid and widespread burst of new star formation within the ring. The result is a stunning galaxy that looks precisely like a donut, intensely bright around its edges, where the new stars are forming, with a relatively clear or empty space at its center where the intruder passed through. The appearance of ring galaxies can vary. Some exhibit remarkable symmetry, with a nearly perfect, glowing circle. Others are more warped, elongated, or off-center, betraying the specific dynamics and angle of the collision that created them. They are relatively rare objects in the universe, but when found, their unique morphology is unmistakable. Unlike spirals, whose arms are thought to be more transient patterns, ring galaxies bear clear and dramatic evidence of a violent, disruptive past. Yet, despite the chaotic event that formed them, these ring galaxies can remain remarkably stable for long periods. The stars within the ring continue to rotate in a balanced way, tracing the aftermath of a collision that may have happened a billion years ago, or even more. They are quiet, luminous monuments to cosmic violence, transformed into objects of striking beauty. These unusual shapes remind us that galaxies are not just static forms, they are dynamic systems whose appearances can be dramatically altered by interactions, leading to new and unexpected structures that persist for eons. Elliptical galaxies represent a fundamentally different mode of galactic structure and stellar motion compared to spiral galaxies like our Milky Way. While spirals are characterized by their flattened disks and organized, sweeping arms, elliptical galaxies are quite distinct. They typically appear as rounded or oval-shaped, diffuse clouds of stars, lacking any clear disk, spiral arms, or significant amounts of gas and dust. But the most profound difference lies in the way their stars move. Inside an elliptical galaxy, the motion of stars is far more chaotic and random than in a spiral. In a spiral galaxy, most stars orbit the galactic center in roughly the same direction, confined to a relatively flat plane, moving in orderly, circular or slightly elliptical paths. In ellipticals, however, there's no overall sense of a dominant rotational direction. Instead, the stars move in highly varied, random orbits. Some might be moving in somewhat circular paths, others in long, elongated ovals, and these orbits can be oriented in almost any direction, tumbling and crisscrossing throughout the galaxy's volume. This inherent randomness in stellar motion is a key clue to how elliptical galaxies form. Many, if not most, are believed to be the product of galactic mergers. When two or more spiral galaxies, each with its own organized stellar disk, collide and combine, the gravitational forces involved can completely disrupt their ordered motion. The gas clouds clash, triggering bursts of star formation, but the overall gravitational turmoil scrambles the individual stellar orbits. Over immense stretches of time, the combined system settles into a more spherical or ellipsoidal shape, largely because the stars are now moving in such a wide variety of paths that they fill out a three-dimensional volume rather than a flat disk. Elliptical galaxies are often older systems with a population of predominantly red, aging stars. They typically contain very little cold gas or dust, meaning that new star formation has largely ceased. The light they emit is smooth and even, like a calm, luminous haze, because the stars are so uniformly distributed and their motions so randomized. There are no bright, active star-forming regions to create vibrant patches of blue light. Inside, though, despite the outward appearance of calm, every single star is on its own unique journey, a quiet, intricate storm of individual motions, all held together by the immense, pervasive force of gravity. These galaxies are the quiet elders of the universe, bearing the marks of a tumultuous past that has settled into a serene, yet internally complex, existence. Not every galaxy fits neatly into the grand, organized categories of spirals or the smooth, rounded forms of ellipticals. There's a third major type, known as irregular galaxies, and they often look exactly as their name suggests: messy, disheveled, stretched, scattered, and uneven. They appear like torn clouds of light, glowing softly across the dark canvas of space, devoid of a clear central bulge or well-defined spiral arms. These irregular shapes are frequently the result of dramatic events in a galaxy's past. Many irregular galaxies formed after close gravitational encounters or outright collisions with larger galaxies. The powerful tidal forces exerted during such interactions can pull a galaxy apart, disrupting any ordered structure it might have once possessed. Its stars and gas clouds are flung out, twisted, and distorted, leaving it without a coherent, symmetric form. Other irregular galaxies may have simply formed in a more chaotic manner from the very beginning, never developing a strong central gravitational pull or a clear rotational plane that would lead to a more organized shape. They might be smaller, primordial fragments that never fully coalesce voids, immense, dark expanses that are almost entirely devoid of galaxies, gas, or even dark matter. Some of these voids can be tens, or even hundreds, of millions of light years across, representing truly colossal stretches of emptiness. Within these voids, you might find a few stray, isolated galaxies, cosmic hermits drifting slowly through the silence. But for the most part, these regions are silent, dark, and still. They are the emptiest places we know in the universe, profound stretches where the cosmic tapestry seems to unravel into nothingness. The formation of these cosmic voids is directly linked to the formation of the cosmic web, just as gravity pulled matter together into filaments and clusters in the early universe. It simultaneously drew matter hours away from other regions, leaving behind these dense areas. Over billions of years, as the universe continued to expand, these already sparse regions became even emptier, growing larger and more expansive. Studying these voids is incredibly important for astronomers. They provide crucial insights into the expansion of the universe and the mysterious force known as dark energy, which is thought to be responsible for the accelerating expansion of space. By examining the distribution and evolution of these voids, scientists can gather data that helps them understand the fundamental properties of our cosmos. In a way, the voids are just as defining of the cosmic web as the galaxies themselves. They are not merely the empty spaces in between. They are an integral part of the universe's large-scale structure, giving shape and definition to the luminous filaments that surround them. They are quiet, dark, and largely untouched by time, representing the profound emptiness that contrasts with the rich, glowing structures of galaxies and clusters. These voids are a silent testament to the vastness and varied nature of our universe, where emptiness itself is a fundamental component of the grand design. While most galaxies exist within groups, clusters, or along the visible filaments of the cosmic web, there are some that choose a path of profound solitude. These are the cosmic hermits, galaxies that drift in almost complete isolation, far removed from any dense cluster or prominent filament. They are systems that navigate the vast emptiness of space with no close neighbors, seemingly uninfluenced by the gravitational tugs and interactions that constantly reshape other galaxies. You might find these isolated galaxies at the very edges of the immense cosmic voids, or sometimes even deep within them, silently traversing regions where matter is exceptionally sparse. Without nearby galaxies to pull at their arms, to collide with, or to trigger bursts of star formation, these solitary systems tend to evolve more quietly, at their own unhurried pace. Their shapes are less likely to be disrupted by tidal forces, and their precious gas reserves remain largely undisturbed, allowing for a more serene and continuous process of star birth, if it occurs at all. The precise origin of these cosmic hermits remains a subject of scientific inquiry. Some might have been ejected from dense galaxy clusters long ago, flung out into the intergalactic void during violent interactions or mergers. Others may have simply formed in regions of exceptionally low density from the very beginning, never having had the opportunity to gather into larger groups or clusters. Whatever their specific history, they move through space as lonely travelers, true individualists in a universe where so much seems to be connected. In a cosmos where galactic interactions are a constant, shaping force, these isolated galaxies stand out. They remind us that even on the grandest scales, solitude is a real and existing condition. They offer a unique natural laboratory for astronomers to study galactic evolution in its purest form, largely free from external influences. Their quiet existence poses fascinating questions about the conditions under which galaxies can form and survive in such desolate environments. They are silent, self-contained islands of stars, drifting in the immense, dark ocean of space, a poignant reminder that even within the vast, interconnected tapestry of the universe, there are still places for quiet, solitary existence. When the Hubble Space Telescope was launched into orbit, it revolutionized our understanding of the universe. One of its most iconic and profound contributions came in the late 1990s when astronomers decided to point it at a seemingly unremarkable patch of sky. This region was deliberately chosen because it appeared to be completely empty, with no bright stars or known galaxies, just a dark, quiet expanse. Hubble was left to observe this tiny sliver of sky for days, gathering every faint photon of light. What came back was nothing short of astonishing. The resulting image, which became known as the Hubble Deep Field, and later even more dramatically, the ultra-deep field, revealed thousands upon thousands of galaxies, packed into a minuscule speck of sky. It was a revelation that transformed cosmology. It showed that no matter where we look, even into what appears to be the deepest, emptiest void, space is teeming with galaxies. Every tiny pinprick of sky, no matter how insignificant it seems, holds multitudes, stretching back billions of years into cosmic history. Some of these galaxies were relatively large and bright, closer to us in time and space. Others were incredibly faint smudges, ancient, tiny systems whose light had traveled for more than 13 billion years to reach Hubble's sensitive detectors. But together, they painted an incredibly rich and deep picture of the universe. The images revealed the sheer abundance of galaxies, their diverse shapes, and their evolution across cosmic time. This groundbreaking observation fundamentally changed our perception of the cosmos. What once seemed like vast stretches of emptiness was suddenly illuminated as being full of light, intricate structure, and profound depths of time. The deeper Hubble looked, the more it found, proving that the universe is far richer and more complex than anyone had previously imagined. These images were more than just pretty pictures. They were windows into the universe's past, revealing the richness and depth of a cosmos that constantly reveals more of itself to those who patiently look.